fourth chapter in the differential protection session is a look into busbar differential protection. Simplest approach is this: you have a single busbar with a number of feeders, and then the application of the differential protection is pretty easy. We typically use the traditional scheme. That means we calculate the differential current and the restraint current. In busbar protection, we use this, we apply the differential concept with instantaneous values. That means we use just individual samples, and with the samples we calculate the differential current and the restraint current, and then we go into the tripping characteristic. And it looks very easy if you look at such a busbar. Of course, we have to do that phase by phase. We have no problem with transmitting measured values over 50 kilometers. We have no problems with vector groups and all these things we discussed before. So for busbar protection, it looks pretty simple, but there are a few things also to consider here which make life a bit more interesting. One thing is, we will see we will have some special challenges in the algorithm. And the point with busbar protection is, if you have a wrong operation in line protection, it's not good. Your boss maybe will ask you a few questions. You lose one line, but normally it's not such a critical thing. If something goes wrong in a busbar protection, if you have a wrong trip in a busbar protection, you lose many lines. You lose all lines connected to that busbar. That means anything going wrong in busbar protection typically has much higher impact on our power systems. So busbar protection must be handled pretty carefully, and we will see we have some challenges in the algorithm. The topology of the plant is typically not that easy, as you see that in this picture here. Plants can be double busbar, triple busbar, and there are a few other things you have to take into account. And the last thing is also, if you have an outdoor substation, it can be a big substation where the distances are long, so you have to make up your mind where are you going to arrange the components. So let's first of all look into the challenges of the algorithm. I will start with a few examples. That is the characteristic we use. You see it's a little bit different from this symbolic thing I normally use. That is the characteristic we use, and in this case our characteristic is very simple. We just have a slope of our tripping area and near the origin a certain cutoff thing. You also see the 45-degree line. If we have a fault on the busbar, we are on the line. So let's discuss the different cases. First of all, the internal fault. We calculate the differential current, we calculate the restraint current. In this case, both are equal, and we are on this 45-degree line, internal fault, clear in the tripping area, we will trip. That's easy, that's normally work. Again, in busbar protection, normally the problem is always avoid wrong tripping, not to trip in case of a fault. That is typically the easier part of the story. So let's look at an external fault. We have here the busbar. We have a fault in one feeder, and that means we have fault current, in this case, coming via the two feeders to the busbar and then flowing into our external fault. That means the current transformer in the rightmost feeder sees outgoing current equal to the sum of the two other currents. That means if we calculate the differential current, I1 plus I2 plus I3, I3 is minus I1 plus I2, so the result is 0. That means the differential current is 0. The restraint current is I1 plus I2 plus I3. That means our operating point is somewhere there on the horizontal axis. Easy, no trip. We are clear outside the tripping area. And now let's assume what can be the critical situation for that. The critical situation is you have a big bus bar with a high short circuit power. And on this bus bar you have one auxiliary feeder which does just some local supply. That means you have a pretty small current transformer. And if you now have on this feeder an external fault, that means the whole short circuit power of the bus bar goes through our poor little current transformer for the auxiliary feeder, and it drives it within a very short time into saturation, and the output signal of this current transformer will look like this. You see here in black the current it should show, but after a few milliseconds it says, oh, too much current, output is 0. To make it simple, we can say after some time the output of this current transformer is 0. What does that mean for our protection relay? Without saturation we had differential current is I1 plus I2 plus I3. The sum was 0. Because I3 was minus I1 plus I2. If we now have saturation, we assume the current transformer at feeder 3 doesn't give any output signal because it's in saturation. Then the differential current, we calculate from that, because now I3 is missing, is only I1 plus I2. Also the restraint current is I1 plus I2, and that means our operating point now moves from here up into the tripping area based on this saturation effect. And that, of course, is the thing which has to be avoided. Now we have a short circuit on an outgoing feeder, and we would expect that the outgoing feeder protection trips and not our bus bar, because then we would lose the whole bus bar. That means we must do something in this situation to avoid a wrong tripping. And that is a challenge for the algorithm. And what you can, or what we normally do in this situation, is we look at the very first milliseconds. That means we assume that in the first few milliseconds there is no saturation of the current transformer. That means we look at this point here, and from there we make a decision. And if in the first milliseconds it looks like an external fault, differential current is 0, and then suddenly our operating point moves into the tripping characteristic, it's very likely that it is a saturation effect. And that means we should somehow block the algorithm. That means we first see an external fault and suddenly this thing moves into the characteristic, then we block it. But also there we must always be careful with blocking. Because we can also have the situation that we have an external fault, maybe there is an exploding current transformer or whatever, and the parts fly onto the bus bar, and 10 milliseconds later this external fault evolves to an internal fault. And if we then block the busbar protection, we would not catch the internal fault. That means this blocking is always a little bit a critical thing. What we typically do is we make this decision before the first saturation comes. That means we have some requirements to the current transformer that we must have a saturation-free time of a few milliseconds. You find this requirement in the manual. And then we do blocking of a fast algorithm, and we activate then algorithms with longer data windows, which are not that sensitive on saturation. You can do some 2 out of 2 measurement or whatever, which avoid wrong tripping on one side, but on the other side, they allow, if the fault really evolves from an external fault into an internal fault, which allow, in this case, a tripping of this internal fault. Maybe a little bit delayed, but it should still be tripped. You see, there is some challenge in the algorithms there, especially because normally the requirement for busbar protection is it should be very fast. We are talking here really about milliseconds. We have for the reaction time, of course, you have to add to that before you have the tripping time, the breakers have to open and so on. But busbar protection is the type of protection with really the highest requirements concerning tripping time. That were the challenges concerning the algorithm. Another challenge is concerning the topology of the plant. And this can be very different. It can also be very complicated. What I show here is just one step further. Instead of having one busbar only, this is a double busbar substation. And in this substation, you see every feeder has a circuit breaker and has 2 isolators, and with these isolators you can connect the feeder either to the green busbar or to the purple busbar. And of course, in such a substation, you would like to have a busbar protection separately for the 2 busbars. That means if you detect a short circuit on busbar A, you would like to trip only the feeders which are connected to busbar A. And the same applies to busbar B. Not if you see a fault on one of the busbars, you trip all breakers around there. That's not a good idea. So we must be selective. Only the affected busbar or only the feeders which are connected to the affected busbar must be tripped. And that makes the whole thing a bit more complicated. And I have indicated this in this diagram. In the current transformers indicated with these circles on the lower part, I have indicated by color to which busbar the feeder is connected. So you see the 2 leftmost feeders are connected to busbar B, to the green one. Then the third one is connected to the purple busbar, and so on. And then virtually we must connect all green current transformers to one algorithm where we calculate the differential current and the restraint current, and all feeders connected to the purple busbar, all these currents are combined into another algorithm. You see here, for instance, this feeder, one isolator is closed, the other one is open. That means we must take into account the position of all isolators to find out, is this measured current now part of the green equation or part of the purple equation? This one would be, this current measured in this feeder would have to go into the calculation for the green busbar, and the other one on this side would go into the calculation for the purple busbar. So it's not really rocket science, but such a busbar can be even more complicated, can even have more feeders. That means you end up in a lot of wiring and contacts and so on, and there is always a risk that something in this topology information is wrong. And now it's important that we avoid that wrong topology information does not lead to wrong trips. That means we must implement in busbar protection a few good ideas to avoid wrong tripping just because of wrong topology information. Wrong topology information means the algorithm thinks the feeder is connected to the green busbar, but in reality it's connected, for instance, to the purple busbar. And the reason for that can be broken wires. No, if it is a big substation, there's a lot of wiring down into the field where you need the position of all the isolators. We can also have failing contacts. These isolators are outside. They may become old and contacts can sometimes fail. So this has to be detected before we make a wrong trip. And we also have sometimes switching actions. For instance, maybe we want to change one feeder from the green busbar to the purple busbar. And that means we start operating circuit breakers and isolators to do these transitions. And that means we have intermediate states. That means states where it's not really clear, is the isolator already connected to that one or is it still with this one? And also these intermediate states have to be taken into account, and the whole protection system must be safe against wrong trips just based on this wrong topology information in these intermediate states. And you can imagine there's a lot of experience which has to go into such a protection technology. One thing which helps us there is the use of a so-called check zone. What is that? I show here again these two busbars, the purple busbar and the green busbar. We set up our equations, differential current and restraint current, separately for the green and for the purple busbar, taking into account the topology information. And the idea is now to define a yellow zone which goes around the whole thing and which calculates the differential current and the restraint current across all feeders without taking into account topology information. And then the tripping condition is we will only trip if, for instance, the purple zone says, I see a fault, I am in the tripping area, and also the check zone says, yes, I also see that fault. I don't know where it is, maybe on the green or on the purple one, but I also see a fault. Then we are pretty sure that there is a short circuit. If only the purple zone says, I see a fault, and the yellow zone says, I see no fault, then there is a certain risk that the fault indication results from a wrong topology. So the check zone, which is a standard feature, helps us to avoid wrong tripping because of wrong topology information. So that was the second challenge we have. And the third one is an easier one. That is the question, where are the components? And I show here in these two pictures the possibilities we have. On the left hand, we see a centralized busbar protection. That means we have one device, one protection relay there, and all current transformers, all contacts from isolators and so on. In this case, it's even a triple busbar thing. Everything is wired to our single device. This can make sense, or this makes sense for maybe smaller substations, especially for indoor, where the distances are not that high. That's called the centralized protection, because everything is wired to one central point. On the right side, you have the so-called distributed busbar protection. What is the difference there? The equation for differential and restraint current, they always have to be done on a central point. That means we must always have one device where everything comes together. But for the distributed busbar protection, the data acquisition is distributed, decentralized. And what helps us there, that in the feeders, for the feeders, we need feeder protection anyhow. There can be distance protection or overcurrent protection or whatever. That means we already have protection relays there who do the data acquisition. Or we install a separate device just for data acquisition for busbar protection, like we had it, for instance, in the previous generation. And then we have a communication system which delivers everything, all sampled values, to the central point where we run the protection algorithm. In the previous generation, we had there a star connected thing. That means we had point-to-point connection from the central unit to all feeder units. With CProtect 5, we have now this ring-type communication available because we make there use of modern process bus technology. You need a redundant high-speed optical fiber, but it's powerful enough to calculate, to bring all the sampled values to a central point, even for a bigger substation. And you see, this reduces the amount of copper wiring if the feeder units are located closer to the switchgear. That means it depends a little bit on the layout of the plant, whether you take the centralized or the distributed concept. That was a look into busbar protection. And with that, we come to the end of the differential protection session. Thank you for listening.